All right, our second current electricity video is going to be on simple circuits, and it's really what most of the unit is going to be about. So, in order for current to flow, the following is necessary. We need a battery, power supply, or it could be the outlet in the wall, something to provide voltage. Remember, the fancy word for voltage is electrical potential. The second thing we need, so if I have a battery just sitting there, there's no current flowing, the electrons want to get from the negative side around to the positive side of the battery. We would say current is flowing the other way from the positive to the negative. But in order for current to flow, we have to connect those with wires. So we need a closed circuit. It's a complete path from current to flow from the positive to the negative side of the battery. And all circuits will have some resistance to the flow of current. So when we look at a simple circuit, we can diagram it basically like this. We have our battery or our power supply. Here, we are going to connect it with wires to some resistance. Okay, which we can represent as a resistor. Now, I said that all of our circuits in our homes, basically, we can simplify or think of as something like this. We don't have batteries, but we have outlets, power coming from the outlets. The outlets are 110 volts. They're providing the energy. And then the resistor is the thing that is using the energy. So it could be a light bulb, it could be a washing machine, it could be a TV set. But everything in our house, all the electricity we use, can be simplified down to this type of simple circuit. Now, other circuits, we can define an open circuit. A circuit that has an opening or a gap, so maybe something like this. Okay, I got my resistor, but there is an opening in it. Okay, and in that case, no current can flow because the electrons can't get from the negative side around to the positive side. Another one is a short circuit. The diagram for that might be this. It looks just like a regular circuit, except for there is no resistance. If there's nothing to resist the current flow, the current will get huge. Okay, and that's bad because it can cause a fire. So, you don't have to draw this, but I'm going to draw it over here. An example of that might be, here is your outlet, and you have a wire hooked up to a lamp. So here's my lamp. All right, now in that single wire, there's actually two strands. So, like this. Okay, so the current's coming in one side of the outlet, flows through one wire, goes through the lamp to light it up, and then goes back through the other wire. And the resistor is the lamp. Now, you may have heard that you should never put a cord, say, going underneath the carpet. And that's because, let's say that these two wires are separated by some rubber insulation. But if you walk over those wires, fray them, wear on them for a while, maybe that insulation will get worn away and there can be a connection here. Now, the electrons going through this wire, they get to this point and they have a choice. They can go through the lamp, which has a lot of resistance, or they can take a shortcut and just jump over to the other side to get back. And they're going to choose the path of least resistance. So they're going to go through this shortcut where there's no resistance. There's no resistance, the current's going to get huge, and the wires get really hot and maybe start a fire. Now back to notes that I want you to take. Mathematically, Ohm's law relates voltage, current, and resistance. So we're going to write it this way, V equals IR. You might see it this way. Okay, it's the same thing. This physically tells you what's going on a little bit better. The bigger the voltage, the greater the current. That makes sense. The more energy I'm putting into it, the more current I'm going to get. And the bigger the resistance, the less the current. They're indirectly related, or inversely related. So, and that makes sense. More resistance to current, it's harder for the electrons to flow through, the current's going to go down. Now, graphically, V and I are directly related. Okay, so I'm going to put V over here, I down here. And since it's a direct relationship, it's going to make a straight line like that. Okay, I'm going to rearrange this a little bit. I get V equals IR. We're saying V is proportional to I. That's why it's a straight line. And what's the slope of that line? Well, the slope is what we took out, so the slope is going to be the resistance. So since this is a straight line, it's constant resistance. So something that obeys Ohm's law is going to make that type of graph. Now, if something does not obey Ohm's law, if for some reason the resistance changes as you change the voltage, it's usually because things heat up, and when they heat up, the resistance can change. It might look like this, being a curved line. So, in a simple circuit, a current of 2 amps flows when the potential difference is 6 volts. What is the resistance? Okay, so I have V is 6 volts. Current, I is 2 amps. And I'm looking for resistance. So V equals IR. And it seems very simple, but we're going to be using this rule over and over and over again. It's kind of like F equals MA, so get used to using it. We get 6 equals 2R, and then our R would be 3 ohms. The unit for resistance is ohms. I can write it out like that, or the symbol is the Greek letter omega. It kind of looks like a horseshoe. Second example, a 20-volt battery is connected to a 40-ohm resistor. We're going to sketch it and show the direction of the current flow, and then what will be the current in the circuit. So if I sketch it, I have my battery over here, right? And then I'm going to connect it to my resistor. Okay, this is the positive side of my battery, that's the negative side of my battery. We might as well write in some data here. Our voltage is 20 volts, it's a 20-volt battery. And then our resistor is 40 ohms. Okay. Now it says sketch the direction of current flow. Remember, electrons want to flow out of the negative side and then into the positive side. The current is considered positive current flow, so our current is going to come out of the positive side. And that will, what will be the current? V equals IR. So 20 equals I times 40. So that's going to give me I is 0.5 amps. Okay, the last part of this video is going to be about meters, ammeters and voltmeters that are used to make measurements in our circuits. I'm putting it here because we're going to hook up circuits soon in class, and you need to know how to hook up the ammeters and the voltmeters. Ammeters measure current in amps. Okay, that's where the name ammeter comes from. I guess amp meter is a little tough on the tongue, so they shorten it to ammeters. The current must be able to flow through them, so they have little resistance. We can essentially say for an ammeter R equals 0. And then they have to be hooked up in series, which means they're part of the circuit because we want the current to flow through them. So they're going to look something like this. Okay, the current's going to come out of the battery. It's going to go through the ammeter, through the resistor, and back. So it's going to measure it because the current is flowing through it. Now, you could also do it, something like this. Anywhere along where it is part of the circuit is going to be okay. What you can't do is this. You don't put it around things like around that. Okay, not only will it not work and read the current properly, in this case you're actually going to fry the ammeter. Back up here we said that the resistance is 0 for the ammeter. If my current comes out of here and flows to this point right here, when it gets to that point it's going to have a choice. It can go through the resistor and get back to the battery, or it can flow around the ammeter to get back to the battery. It's going to choose the path of least resistance, so it's all going to go through the ammeter. There is no resistance in that circuit, so rather than the wires getting hot, what's actually going to happen is you're going to fry the ammeter. Voltmeters measure electrical potential. Remember, that's just a fancy word for voltage. They have very large, essentially infinite resistance, and they have to be hooked up across or around the thing that we're measuring the potential difference, because we want the difference from one point to another. So if I have my battery here, my resistor here, I can hook up my voltmeter around here. That would give me the potential difference across the battery. Or I can hook them up like this. Voltmeter there, that's okay as well. What you don't want to do is that. Putting it together, if I was to do a circuit with both in it, it might look like this. Now this isn't the only possibility. I could put the ammeter here. Let's say the voltmeter over there.